Bismillahirrahmanirrahim. Today we have in this lecture we have some results regarding to Riemann integration. First, in Riemann integral we take generally take a closed interval, AB closed interval, and then consider a function f(x) which may or may not be continuous, which is bounded on the interval AB closed interval. Today we take a bounded function on AB closed interval, that is, a function is said to be bounded for which a specified value, all the value of the function must be less than or equal to that constant value. We then divide the interval AB closed interval at several points. The set of the point dividing AB closed interval is called a partitioning set, which is denoted by P. The point of the division may be equidistance, but this is not necessary. By changing the mode of the partition AB closed interval, we can get different partition sets, that is, taking the interval size, we can take different partition of AB closed interval. Number third, we then form two types of the sums called upper sum and the lower sum, which are respectively denoted by capital S and small s. Their value for particular partition set is given by capital S is equal to summation k is equal to 1 up to n mk delta xk, and small s is equal to summation k is equal to 1 to n mk delta xk, where mk, capital Mk, is equal to LUB, least upper bound of the function for x belong to specific xk minus 1 to xk close interval, and mk is equal to GLB of the fx, greatest lower bound of the function for a specific interval x belong to xk minus 1 to xk close interval, and that delta xk is equal to xk minus 1, that is the length of the specified interval or width of the interval. Number 4, since we have a large scope of the variation in partition sets because of the fact that between any two real number there are infinitely many real numbers. So for different type of the partition we have two sets, the set of the all capital S upper sums and small s, the set of all small s. We will get a sequence S is a set of all possible upper sums for all the possible partition of AB closed interval, and we get second lower sum sequence is a set of the all possible small s of all the possible partition of AB closed interval. Fifth number, we then find GLB of the capital S and LUB of the lower s. For the different partition we get the different capital S upper sums. So from the different capital S we can get GLB, greatest lower bound, and similarly for the lower sum, for different partition we will get different lower sums, and from different lower sums we will get a one LUB, least upper bound, which we denote by J and I respectively. It means that J is equal to GLB of the upper sum and I is equal to LUB of the lower sum, and then the value is given by J is equal to integration a to b fx dfx. On B is there is bar that represent the upper sum, and I is equal to integration a to b fx dfx, and B is A is underlined. It means that is the for lower sum. Since I and J are the LUB and GLB of the certain set that is small s and capital S having the unique value, and they are named as upper integral, lower integral. Now sixth number, we say that a function f(x) is Riemann integrable on ab close interval and briefly integrable on ab close interval if I is equal to j. If I is equal to j, it means that the function is Riemann integrable, and if I is not equal to j, then the function is not Riemann integrable on ab close interval. Now if m is equal to LUB of the function in the ab close interval and small m is equal to GLB of the function f(x) in ab close interval, and mk is equal to LUB of the function in xk minus 1 to xk close interval, and small mk is equal to GLB of the f(x) in xk minus 1 xk close interval. Then relation between capital M, small m, mk and small mk is given by m is less than or equal to small mk, and small mk is less than or equal to capital MK, and capital MK is less than or equal to capital M.